Hello, everyone, and welcome to today's webinar, The Art of High Energy CT, presented by VJ Inspection Services and Datest. I'm Bob Maziuk, and my co-presenter today is Domin. We will be doing a Q&A session at the end of the presentation utilizing the chat function. So you can use the chat button at the bottom of your screen to submit your questions to me. The default is to send the chat to everyone. So if you don't select my name, your question will be submitted to every participant in the webinar. So if we don't get to all questions today, we will answer everyone via email after the webinar. We will also be displaying our contact information at the end of the webinar should you have any questions or need additional follow-up. And to eliminate background noise, we ask that all participants mute their phones. Thank you. So just a short description before we get started on what we're presenting today. We're basically going to illustrate how we were able to leverage our experience using techniques we've developed for inspecting such items as rocket motor fuel nozzles and additively manufactured aerospace and spaceflight hardware to inspect a 17th century Tibetan sculpture, VJIS and consort VJIS. So we'll go ahead and get started here. Founded in 1987, VJ Technologies is now a world leader in the design, manufacture, and installation of state-of-the-art X-ray inspection systems. These systems utilize digital imaging and computer tomography techniques. The industries served and supported include nuclear, aerospace, defense, automotive, and electronics. So this will be the first in what will be a unique series of webinars featuring innovative DR and CT inspection techniques. The VJIS and Datest inspection service labs span across the country. In East Haven, Connecticut is the high energy facility where Alex and I reside. We're known in the aerospace community for offering high energy digital radiography and CT solutions at energies that range from 160 kV microfocus to 9 MV. Our certified engineers can perform, read, and report on DR and CT scans to meet all known regulatory, industry, and internal requirements. This is a view inside the facility where we did this project. We talk a little bit about these capabilities a little later on, and looking from the source to the detector. So due to the sensitive nature and confidentiality of our typical customers, either space flight or defense or aerospace hardware, most of which is covered by our ITAR restrictions or other confidentiality agreements, we are unable to share actual images of a lot of these items. So what we decided today was to include the examples of some commonly found indications uncovered in additive manufactured parts and lead into that with how we've utilized these techniques to do the imaging of this ancient sculpture. So as we look at these images, to the left, we've got some selective laser melting flaws, which are fusion flaws. This could be due to malfunction of the laser or misalignment or a skip. There's any number of things that can cause something like this, but it is in fact a detriment to an actual part, and this was created for us as a coupon to be able to see what exactly the indications would look like. On the right, we have a condition of trapped powder in a channel that should be open for either airflow or fluid or whatever, and this is something that the manufacturers and end users need to be aware of as well to be able to either clean it out or not use the part. In this next figure on the left, part of that clean out process will utilize different fluids, and this is an indication of where fluid actually got trapped in the passage from the clean out process. So it's another area of interest here. And on the right, we have a couple of other examples of fusion flaws that would, again, be detrimental to a piece of production hardware.
Yeah, so just like Bob mentioned, because we can't show a lot of the parts that we commonly deal with because of ITAR confidentiality agreements. We thought that it was a great opportunity for us to inspect the priceless artifacts and be able to show some images of exactly what we do in East Haven. So late in 2018, VJIS became acquainted with a renowned conservator, Abigail Hyken. She's from the Museum of Fine Arts, Boston. Ms. Hyken brought us a very unique request to CT scan an ancient bronze Tibetan sculpture. Vajrabhira, with consort Vajravitali, has a primary face resembling that of a buffalo and 16 arms on either side. He wears a crown of severed heads and stands on prone bodies of Hindu deities and animals. The sculpture was presumed hollow and made of several parts copper and brass alloy. The goal of the CT scan was to determine if the hollow body had any religious contents, such as scribes, relics, or other items often encapsulated in such sculptures. So as you could probably imagine, transporting a sculpture is not very easy. So before the museum invested too much time and resources into this endeavor, they wanted to be made comfortable in knowing that we would be able to achieve their intended result. So Ms. Hyken and the Museum of Fine Arts Boston sent over 4 copper, steel, and brass fittings sealed with one or more objects inside, and our goal was to identify as many of the objects as we could. So for this proof of concept, we gathered the fittings and placed them in a circular fashion with about 30 degrees of separation to minimize the amount of overlap from one to the other. So here, when we got the results almost immediately, the things that stuck out to us almost immediately, we have a wooden clothespin, a binder clip, a fishing fly hook, there was glass file, and also a wooden furring strip stamped with the letters MFA. So upon completion of our proof of concept scans, Ms. Hyken sent us a photograph of the contents. So like we just saw on the previous slide, the most identifiable objects were the fishing fly hook, the wood stamped MFA, the binder clips, crushed box, a glass file, and a wooden clothespin. Some of the more challenging but still identifiable objects were the origami frog and cotton twill tape. And things that we were just unable to identify but still resolve was the paper with "Thank you, Bob" written on it, a paper with a gray and color scale, and a Museum of Fine Arts business card. So based on these results, the museum concluded that they were satisfied and decided to proceed with the project. Once receiving the sculpture, we had a very strict timeline with access to it only being granted for one 8-hour-long day. And also, the museum had hired professional artwork handlers for positioning the sculpture at our direction. Given those restraints, there was little time to practice with various techniques for optimal outcomes. So we relied heavily on our experience and expertise from working with additively manufactured spaceflight hardware of various materials to optimize the results. Normally, to select the appropriate energy or trigger rate, gain, beam conditioning, etc., we have, a customer acceptance criteria to look at, any specifications, codes, blueprints, the material density and thickness. But unfortunately, in 17th century Tibet, they didn't have an AS9100 Q quality management system, so this was unavailable. To get started, we ran a series of short flyby region of interest scans to narrow down our technique. The flyby scan is really an essential tool that provides us with results within 25 minutes and really allows us to quickly switch parameters in our projects if they're necessary. Based on our results, we decided to go with a technique that utilized the 6 MeV beam. After conditioning the beam to eliminate any potential for ring artifacts, beam hardening, streaking, noise, or scatter, we were ready to proceed. Obtaining 100% coverage of this sculpture was done in 2 scans because of its size. Using our offset scanning technique, we can extend our field of view by up to half of our detector size at any given geometric magnification. For this instance, we only needed an additional 4 inches. and this placed the largest width of the sculpture inside of our field of view, thus ensuring that we acquired enough projection data to reconstruct the 3D model. So here we can see the raw unprocessed images. On the next slide over, we can see our proprietary ADE filter applied to them. So performing one acquisition at the top of the sculpture and one acquisition at the bottom of it, with some overlap in between, allowed us to really align it and stitch the data to achieve that we have true 100% coverage. Here on this next slide, we can see the reconstructed volumetric view of the stitched sculpture. So to really understand what we're seeing inside the statue, we researched how creating a bronze sculpture would have looked like in the 17th century. During our review, we found evidence of the lost wax process. This is a method of casting where molten metal, such as bronze, is poured into a mold that had been created with the help of a wax model. An artist would first create their sculpture using materials such as clay, brush on a thick gelatin-like material, and then apply a plaster encasement. Once that encasement is dry, wax is poured into the encasement and to the artist's desired metal thickness. Molten metal is then poured, and the wax is melted and drained away by use of sprues. For larger statues such as this, a heat-resistant core is placed inside to prevent the molten metal from completely filling the mold. So during the pour of the metal, any tilt or shift in the heat-resistant core could render an unsuccessful result. So therefore, throughout this entire statue, we can actually see the sprues and nails that were placed to hold the heat-resistant core in place and provide passage for the molten wax whilst the pour was taking place and the wax was melted or lost.
So in the end, we didn't uncover any religious content or items of interest that may have been inside the sculpture, but we were able to provide the museum with a lot of interesting detail onto how the sculpture was actually constructed, and we were able to resolve the porosity in the walls and some air pockets that you had seen. Beyond those flaws, some of the most interesting aspects were uncovering some of the techniques and methods used in 17th century sculpture process. So it was kind of a fun project for us. As you know, we had talked about, how does this tie back to what we do in the aerospace world? And as the trials that were sent to us looking for paper and cloth and low density materials through copper and brass and steel were part of the challenges, just like when we're trying to look at the char of a rocket fuel nozzle that's been tested through inches of stainless steel, being able to see relatively low density trapped powder in a very high density nickel-based alloy. So looking through inches of heavy, thick, dense material to resolve relatively small, low density items. And that was similar to what MFA had tasked us with in the beginning, trying to show that we could resolve through brass and steel and copper some of these low density indications. So it enabled us to use a lot of what we were already doing in some of these applications. Okay, just to kind of go over the capabilities basically of our facilities around the country, from 225 kV up to 320 kV or 300 kV microfocus DR and CT, 450 kV conventional DR and CT, 6, 7.5, 9 MV high energy DR and CT, and a little more on the 7.5 MeV later on, a field deployable solution as well. So here in the high energy lab, we could accommodate a maximum capacity of a sample with a diameter of up to 5 feet, height up to 8 feet, weight up to 11,000 pounds static load. We utilize flat panel detectors that range from 75 micron pixel pitch to 200 micron, linear diode array with pixel pitch from 0.2 millimeter to 0.4 millimeter pixel pitch. The DR and CT methods that we employ include real-time dynamic imaging, static imaging for our DR applications, For CT, axial, or more commonly known as cone beam or centered scan CT, utilizing offset to increase the available detector width, as well as range extension. As Alex had mentioned earlier, the offset will allow up to a 50% increase of the available detector area. Range extension, we can go up to 5 times the detector width. We can also do helical CT for taller parts or for parts that require a more centralized beam, and fan beam CT that utilizes a LDA. Limited angle CT is where we come back to the 7.5 MeV portable source, where this can be utilized here in our facility, or we could deploy it to a field installation, as we do pretty regularly. Software functions that we utilize include our ADE and ADEN filters for DR applications, iterative artifact reduction, beam hardening, ring artifact removal, nominal actual comparison, and many other tools that are available in the post-processing of the data. The interpretation and reporting that we do is done by NAS 410, ASNT Level 3 and Level 2 qualified personnel to AS 9100, ISO 9001, and pending NADCAP quality programs. So at this point, we would like to turn it over to our participants to ask any questions that you might have, and we'll address those. And as we said earlier, if we don't get to any of those questions, we will follow up via email. And if you prefer, you could just email us your questions privately after. Okay, since that's it for questions, in closing, we would like to thank everyone for attending today's webinar. We hope you enjoyed our presentation and perhaps taken away something of value that may be of use to you for your next inspection project. If you need any additional information or have any questions, please reach out to us at the contact info screen or visit our websites, vjt.com and datest.com. Thank you, everyone.